Hey guys, let's talk about phase portraits in 2D. So we're going to do 3 examples, and we're going to kick it off with the diagonal matrix. You should always do everything with the diagonal matrix first. They're going to give you intuition for how the other matrices act because of eigenvalue decomposition for the most part. There's one little lie there, and that's when you have complex eigenvalues, and then you'll get rotations, but don't worry about it. So, okay, let's start off with this. And the whole reason we're seeing these matrices is because we have a system of equations where you have the derivative of something is equal to matrix times vector. And what I really want you to think of is velocity is equal to some kind of action, think stretch or rotation or something like that, some kind of matrix action on the position. Okay. Now, this is something that we've seen before where the derivative is a multiple of the original function. And, well, let's just write out what it is. So we have something like this. F prime equals AF. And a solution for this would be F is some number e to the AT. Okay? And, yeah, if you were to take the derivative, the A pops down, and you have e to the AT again. And right here is the original copy of F. And so here's AF. And indeed, that's F prime. Okay. This is our whole motivation, and it turns out that in order to define the exponential function, all you need is addition and multiplication, and then you can define it with the Taylor series. And that's essentially what we're going to do, and essentially the solution to this is going to be, at least in some sense, you have some number out front that depends on your initial condition, and you have e to the dt, where d is this diagonal matrix, and so we need to make sense of that. So that's C, don't worry about it. I didn't even really have to write it because the main thing I want to get to is right here. Let's talk about how we're going to define the exponential of a matrix. It's with the Taylor series. So we have this infinite sum, and then we have 1 over n factorial d to the n t to the n. Okay, so that might look terrible the first time you see it, but it's not. So let's break that down even more. Again, there's that C out front. Don't worry about it. And now what this means, so I'm going to be looking at this diagonal matrix here. And d to the n, this is only true for diagonal matrices. You can just put that in as the exponent on the main diagonal. Okay, so that's not so bad. And these things, so t to the n and 1 over n factorial, anytime we just have some number in front of our matrix, that just means that you should distribute it to all of the entries. And notice what happens is we just don't care about the 0 entries. Okay, so what's going on if I were to write this all out? Well, that d to the n is 3 to the n. This t to the n gets us a t to the n, and this 1 over n factorial is 1 over n factorial. And our new matrix looks like this. Okay. And if you add this all up from n equals 0 to infinity, the way you add matrices is you do it term by term. So if I had a, b, c, d plus x, y, z, w. Then in the 1, 1 entry, you add the 1, 1 entries, so it'd be a plus x. Then in the next entry, whatever that is, whether I'm going to the next row or next column, so I'll have b plus y, and down here I have c plus z, and then I have d plus w. Okay, you just do it component-wise. Okay, so this becomes c. And basically, when we add these all up, that just takes place inside each component. So now I have 3 to the n, t to the n, n factorial, 0, 0, because we're adding up a bunch of zeros. And then the sum minus 2 to the n, t to the n over n factorial. Okay? So this sum popped inside. And now we should be able to recognize this object if I wasn't lazy and wrote down the limits. Okay, now we should be able to recognize this object. This is that multiple out front, that the thing that depends on our initial conditions. And now we have e to the 3t, 0, 0, e to the minus 2t. Okay, so we began with the diagonal matrix. Here it is. And we end with the diagonal matrix, but this diagonal matrix is a function of time. And if we think about how it acts, so this is if we have input space and then over here to output space. If you are I hat, okay, here's my I hat, then the original diagonal matrix, it would scale I hat by a factor of 3. It would stretch it by a factor of 3. But now I stretch it by a factor of e to the 3t. So if t is 0, this is the identity matrix, because both of these things on the diagonal become 1, right? If t was 0, this would be a 1, and this would be a 1. If t was really big, and in fact, as t goes to infinity, this just gets stretched and stretched and stretched. It gets pulled away. And this is where it kind of depends on our initial condition. So if my dot was lying here, then this matrix, which, look, how do we begin? This is this, right? Those two things are the same. I follow this chain of equalities. So I'm going to write e to the dt. And then this c, I really should write out c vector. Okay, we could put a little vector there. And so it could be something like this dot. It's you should think of it as your initial condition or your initial, position. Okay? And then we're going to update this with the e to the dt. Okay, so that dot would get stretched somewhere. But if your dot was in the negatives, you get multiplied by a really big number, you get a really big negative number. If your dot was over here, okay, well now what's going to happen? Now the e to the negative 2t influences it. So again, if t was equal to 0, this is a 1, and it stays where it is. But if t was something really large, then this dot is getting pulled down to 0 because this whole number is getting pulled down to 0. So we have flows that look like this. If our dot was in the negative y-axis, it still gets pulled to 0. Okay, so anyway, this object over here is our phase portrait. Let's go ahead and label it phase portrait. And I can still add more, but it's kind of the backbone of our phase portrait. So now we imagine, what if the dot was somewhere over here? And in fact, I'll just add it over here. Well, now the idea is it just flows as if both arrows were kind of acting on it. And so it would end up flowing like this, but the velocity vector right here is something like that, whereas the velocity vector right here is something like, I'm just trying to draw the tangents, something like this. So, if I was here, the red vector is going to pull me this way some amount, the blue vector is going to pull me this way some amount, and the net effect is going this way. And then if I was here, same idea, net effect, net effect. Okay, so the way we draw that, we just do one smooth little curve to resemble what a flow would look like. Okay, and the flows just kind of are a combination of the blue and red. Okay, so there's our phase portrait. All right. Now, I feel like we've lost track of where we came from, so let me back up and talk about the phase portrait one more time. But, this is really saying that the velocity is equal to how this D matrix acts times our position. So this is our position, is equal to dx. Okay, so if right here is x, then what does our D matrix want to do? It wants to scale the x component by 3 and the y component by -2. So that the scaling of the y component by -2 is what's pulling it down that way. The scaling of the x component by 3 is what's pulling it this way. And the net result is something that moves right more than it moves down, but it kind of does both. Okay. Now, I really should abandon all of this because the goal is to have a phase portrait, and I really could have drawn what I just drew over here. I could talk about there's some down component, there's some rightward component, and the end result moves more right than it does down. And that's especially true the lower you go. So by the time I'm here, I get really pulled to the right and only a little bit down, and I'm basically moving to the right. Okay, so that's what these flow lines are, and that's because what I'm drawing is my velocity vector. How do I find my velocity vector? I do this computation. What does this computation say to do? It says you stretch the x by 3 and you flip over the y and scale it by 2. So one more time, if I was here, my x is negative, I stretch it by 3, so I get pulled more negative, and my y is negative, but I flip it, so now it's positive, and my end result is something like that. And, I probably could have drawn these flow lines better, maybe it's something like that, whatever. Okay, so that's a phase portrait. Now let's do it for a non-diagonal matrix, and the whole thing is to diagonalize it. So this matrix has been beaten to death in class and in my little talks. So we know from the last video that this is equal to eigenvector, eigenvector, eigenvalue, eigenvalue, and then the inverse of the eigenvector matrix. So 1/2 minus 1/2, 1/2, 1/2, boom. I'm going to call this V, D, V inverse. All right. Now, the whole point of eigenvector decomposition is your original matrix behaves like the diagonal matrix, but not with respect to I hat and J hat. It's with respect to first eigenvector and second eigenvector. Okay. So let's draw a phase portrait for this. It looks very similar to the last one, but it does not move along I hat and J hat. So we need to draw, here's my V1 axis, so to speak. Here's my V2 axis. You should watch the last video if that's confusing, but just really quick, this 1, 1 vector, here it is, and then I just scale it as much as possible. So positive scaling moves this way, negative scaling moves this way, okay? All right, now, and similarly, this vector, that's this one, positive scaling moves northwest, negative scaling moves southeast. Okay, oops, wrong thing. I wanted to undo that arrow, great. Okay, now, for this line, we get stretched by a factor of 3. So if I'm negative, I'm more negative. If I'm positive, I'm more positive. For the red line, remember, this corresponds to something that's going to have like a e to the minus t, e to the 3t, and this thing is going to pull us down to 0. So we're going to get compressed here. Okay. And now it turns out our phase portraits end up looking like this. Flow, 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 flow. And it's exactly like this last one. It just got rotated where instead of caring about I hat and J hat, or the X and Y axes, we care about this 1, 1 and this minus 1, 1. And ignore me for a moment. The coffee's very strong. Sorry, I just kind of went crazy. Oh, nice. Okay, perfect. So, all right, back to the video. You guys are good at quality in this class. All right. I'm going to jump ahead a little bit of where the course is going, but just to give you all an idea of what to have in your head during class and stuff. So let's talk about e to the mt, where this m is this matrix M. And it's defined the exact same way, okay? This infinite sum, m to the power n, t to the n. But you want to think of it in terms of this decomposition, because it turns out that m to the n is, so when I write that v, I'm talking about this matrix here, so 1, 1, minus 1, 1. And then we have that diagonal matrix, which I'll write out. And then we have v inverse. And notice this power is what I put on the diagonal, but it doesn't really affect the v's. And the reason for that is if I were to write, oops, not m, d, v inverse. So here's one copy of m. Here's another copy of m. So if I multiply everything, this is m squared. And right here, we have a v times v inverse. These cancel. They're the identity. It's like writing 1. Just forget about it and squeeze everything together. So I have d, v inverse. And notice what happens. We get d squared v inverse v. And so the power kind of just jumps to the diagonal because the middle v's are going to cancel with the v inverses. Okay, and what this lets us do, you should just think of this like distributing. Essentially, if you work it all out, this v here gets pulled outside of the sum on the left, and then there's another v inverse that gets pulled out on the right, and in the middle, you have this thing that looks just like our last example where you have a diagonal matrix, raise the sum power, 0, 0, minus 1, to the n, t to the n, boom. And I could have put the n factorial on the inside, but I just didn't, okay, whatever. And so, all right, we have v, when you simplify this all out, you'll have e to the 3t, 0, 0, e to the minus t, and then v inverse. And, okay, this should be very reminiscent of this. And if you let t just begin from, t equals 0, move along the t heading towards infinity, so you just grow and grow and grow, it's telling you how we're just going to get stretched way out in the x direction, whereas the y direction, there becomes less and less movement. So these flow lines would be kind of stuff like that. But up here, it's x and y. Over here, that movement, so now I'll plug back in what my v is, 1, 1 minus 1, 1, okay? The 1, 1 axis, so to speak, is going to get pulled out towards infinity, whereas the perpendicular axis, the minus 1, 1, gets compressed down to 0. And that's exactly what is being said here. We get compressed down to 0, we get pulled out to infinity, okay? All right, cool. So hopefully that's making some sense, even though it's still rather hand-wavy, but, you know, we don't have linear algebra as a background, so. All right. Last matrix. The reason this one's labeled N is because it has a null space. What a fancy word. All right, let's talk about it. So we have 1, 2, minus 2, minus 4, minus 2, minus 4. And notice that row 2 is a multiple of row 1. I multiplied by minus 2. You can also think of it as column 2 is a multiple of column 1. I multiplied by 2. And what both of these pieces of information are trying to hint at is that there's redundancy in this matrix. And a redundant matrix is something whose determinant is going to be 0. So I called this matrix N. Okay, it's going to be 0. And we can check if I did 1 times negative 4, it's negative 4, minus those two things. So negative 2 and 2, that's another negative 4. So I have negative 4 minus minus 4. Okay, I get 0. Now the reason for that, you should watch the last video, but essentially this matrix will collapse a dimension. Okay, so what dimension will it collapse? Let's figure that out. So there is some non-zero vector, okay? This vector is not the 0 vector. And yet, when I multiply it by n, I will get the 0 vector. That's what I mean by collapse a dimension. There's something that it sends to 0. So I just want to clean up these dots, they're bothering me. Okay. All right, so what is it? Look, just stare and figure out how to make this dot product 0. And so I could, you know, this with 1, this with 2, I need to get 0. You stare and you think about it for a bit, and you might end up here. So let's fill that in. Minus 2, 1. And if that was confusing, you could have just written out the multiplication. So if I go across the first row and down this column, when I wrote v1, v2, you'll get v1 plus 2v2 needs to equal 0. This 0 is that 0. Okay, this is just me doing the matrix multiplication where I have v1, v2. Okay? All right. Now, stare at this, solve for the relationship. You have v1 is negative 2, v2, and then just plug something in. If I plug in 1 for v2, then I'm forced to make v1 equal to negative 2. Okay? So, you can do it that way, or you can just kind of stare and know, and I encourage you all to get to a point where you can stare and know, especially in the 2 by 2 case. Okay? All right, so this dimension is the one that gets collapsed to 0. This is moving to the left 2 units and up 1, all right, or moving to the right 2 units and down 1. So here we are, and there it is. This whole line, everything on this line gets sent to 0 by the matrix N. All right, and now if we think about the motion equation we have that x prime is equal to nx, and if x lies on this line, so for example, this spot here, this is 2, negative 1, okay? Notice that lies on this line, you just had to multiply by negative 1 in both entries. That'll make it positive 2 and negative 1. Okay, so if we're here, if this is my x, then when I feed it into n, what I'm going to get is the 0 vector, which means my velocity is 0. So this dot right here is not moving. It's at a steady state. Everything on this line is at a steady state, okay? All right, let's figure out the other interesting component. I'm going to call it the other eigenvalue, but 0 is not allowed to be an eigenvalue, I believe. I have to brush up on my linear algebra terminology. So let's solve for it. So we have 1 minus lambda, 2 minus 2, minus 4 minus lambda. And we want the determinant of this to equal 0 in order to find the lambdas that work. So we have 1 minus lambda, minus 4 minus lambda, and then minus minus 4, so plus 4 equals 0. And we work this out. We have lambda squared. That's from these two. Now this is a positive 4, this is a minus 1, so we have a positive 3 lambda. And then we have a minus 4, but there's a plus 4 here, and that'll equal 0. And those go away. Great, because I want to be able to factor out a lambda. And then I have lambda plus 3 equals 0. This corresponds to lambda equals 0. This is our null space. Don't worry about that word. This is not a linear algebra class. It's just saying there exists a vector that gets sent to 0. And in fact, anything on this line gets sent to 0. Anything on this line. Okay, and then there's also lambda equals minus 3. So let's take a look at that. So 1 minus minus 3 is 4, 2 minus 2. So here I'm looking at lambda equals minus 3. And what's this? Minus becomes plus 3. That's negative 1. Okay, and we have v1, v2 equals 0, 0. And we should solve for it. And I'm going to look at this second row here. So minus 2 copies of v1 minus a copy of v2 had better equal 0. And if you stare at that, then you could do 1 and let's see, negative 2. I believe that works. So let's just double check. If I do this dot product, so this and this will give me negative 2. This and this will give me positive 2. Sure enough, I get 0. Okay, cool. So what is this? This is moving to the right 1 unit, moving down 2 units. So I have to go to the right and then down, I'm here, or I go to the left and up and I'm here. And let's draw this in. Okay, great. So on that blue line, well, let's try and do something like an eigenvalue decomposition. So this matrix N, which is 1, 2, minus 4, is equal to, at least we hope, this is not something, all right, you stack up the eigenvectors. So for the eigenvalue minus 3, I have 1, minus 2. And for the eigenvalue of 0, we have minus 2 and 1. And then that was minus 3 and 0. And if I call this V, then over here is V inverse, which I'm not going to bother writing. Okay, so the whole idea is on this line, on the 1, minus 2 line, so that's my blue line, I have a negative eigenvalue. So when I do the exponential of this matrix, I'm going to get like e to the minus 3t. It's going to compress. It's going to send me down towards 0. Whereas if I'm on the other line, if I'm on this span, that's a 0. Nothing happens. E to the 0t. You just you stay the same. It's like multiplying by 1. You don't move. Okay. So okay, fine. Well, what happens if, for example, I am, I should really be careful here. Let's see. Okay. What happens if I'm right here? Okay. Well, the idea is, and this is why you should absolutely watch the last video. So this position is 1, 1 in terms of I and j. It's 1 copy of I plus 1 copy of j. But how should I write this if I use, so let's see, 1, negative 2, 1, negative 2. So this vector here, okay, that's this vector, I'll call that v1, okay, my first eigenvector. And it turns out if I did a negative v1, so notice v1 points southeast, so negative v1 points northwest, okay. I need 1 copy of negative v1 plus, I also have this motion here, it's 2 units right and 1 unit down. That's negative v2, so if I call this thing the second eigenvector v2, then going this direction is a negative v2, negative v2, negative v1, okay? So it turns out in terms of v1 and v2, I'm taking minus 1 copy of v1 and minus 1 copy of v2. So that's what those are saying. They're saying take a negative v1 and a negative v2. Okay. Now, this component is going to behave like the v2 line, which is to say everything on this line doesn't move. And so this component just kind of, when I say component, that's a bit of a lie. Okay, let's parallel translate this line over here. Okay, so, oops, where am I? Here we go. There we go. Motion on this blue line that I just drew is going to behave like motion on this blue line. So it'll get pulled down to when that coefficient is 0, okay? Which means that the flow is pulling us towards the black line, okay? And that's why I say when this component here is 0, because like this dot corresponds to moving -1 unit of V2. So if we've done that, okay, if we do this motion, we're here. Or I should say we're here. And now I could change this multiple of V1. If I had a positive multiple of V1, I'm down here. If I had a negative multiple of V1, I'm up here. But what they all have in common, everything has in common on this line, is that you have one negative copy of V2. That's how we got to right here. Okay, so that is going to remain unchanged. That gets influenced by this guy. However, whatever number's in front of my V1, whether I'm up here or down here, that gets pulled down to 0 by this guy. And so that's what these arrows are saying. They're saying, hey, move this thing down to 0, but this stays the same. So we're drawn towards a negative V2, which is exactly where this dot is. This is negative V2. If I was up here at positive V2, I do another parallel copy of my line. Okay. And so right here, this red dot, this is positive V2. If I were to add to that some multiple of V1, then negative multiples would be up here, positive multiples would be up here. It doesn't matter because once this matrix starts acting and starts moving around, it's going to behave like this, and that multiple of V1 gets influenced by this thing, okay? There shouldn't be parentheses. I'll just do a little twiddle. Okay, it's influenced by this, whereas that V2 is influenced by this, but this is just the number 1. This is not changing it, okay? So stuff up here gets pulled down, and stuff down here gets pulled up, and it's pulled towards that red dot, okay? The V1 contribution is going to 0 because this is killing it, whereas the V2 contribution is remaining unchanged. That's what this is saying. So we just end up getting a picture. We end up getting a picture of, we sketch out the, whatever. This is our null space. This is our copies of, what is this, -2, 1, something like that. Except we want the span, so I'll just put a C in front. And then we have all these parallel translations of that other line. Okay. And then the idea is you're pulled towards the black line. So stuff above gets pulled down, stuff below gets pulled up. And that's because things over here, there's some copy of V2, which doesn't change, and then some copy of V1, and that number there is going to get pulled down to 0. So it gets pulled down to 0 to where it's just a pure copy of V2. Okay, so those are the different phase portraits we're going to see. The null space one, you get drawn toward the null space, and otherwise you'll look at rotations of a diagonal matrix. All right.